46 billion suns. That's pretty bright. Let's use that brightness to confirm the mass of the galaxy. To start, we'll need a flashlight. If we know the mass of one flashlight, and its brightness, we can figure out the mass of a whole wall of identical flashlights. How? By measuring its total brightness. Let's call it the brightness method. It's another way to measure the mass of objects in outer space. It also helps us understand why Vera Rubin saw the stars in Andromeda moving so much faster than anyone expected. Once you've got the total brightness, compare it to the brightness of the single flashlight. The relationship between the brightness of all the flashlights and just one will tell you how many flashlights there are. Then, multiply the number of flashlights by the mass of one flashlight, and you've got the total mass. We can use the brightness method to calculate the mass of the stars in a distant galaxy within a given radius. But there are a couple of problems. First, some galaxies are farther away than others. For example, Triangulum is farther away than Andromeda. Galaxies that are more distant appear less bright, even though they tend to emit the same amount of light as closer galaxies. But scientists know that, just like the brightness of a flashlight, the brightness of a galaxy decreases in a predictable way, based on distance. When a galaxy, or a flashlight, is farther away than another one, it only appears less bright. So scientists can determine the actual brightness of a galaxy if they know how far away it is. The second problem is that, unlike these flashlights, not all stars are identical. Fortunately, there's a relationship between a star's brightness and its mass that helps account for the different types of stars found in galaxies. Having solved the problem of unequal distance and accounted for different types of stars, physicists determined through the brightness method that the mass of Triangulum within a radius of 400 million billion kilometers equals 7 billion suns. But the orbital method gave us a mass of 46 billion suns. That's a difference of 39 billion suns worth of mass. Similar mass differences have been observed in over 1,000 galaxies. Something very, very strange is going on. But what? The brightness method assumes that all mass in a galaxy emits light, but the orbital method doesn't assume that. In fact, most of the mass in Triangulum measured by this method is unseen mass that emits no light. And because there's a relationship between mass and orbital speed, it's this extra mass that can explain the high speeds in Triangulum and in all other galaxies scientists have checked. Such as Andromeda, where Vera Rubin observed orbital speeds far higher than expected. Most physicists are confident that Andromeda, like Triangulum, is dominated by unseen mass, and they think that this additional mass is responsible for the speed she saw. By looking at satellite galaxies and other distant objects, physicists now think that, in most galaxies, this unseen mass extends much farther than the outermost stars. In this image, we represent this mass by the pale blue shape. Because the unseen mass doesn't emit or reflect any light, it's known as dark matter. The speeds of stars and galaxies aren't the only evidence for the existence of dark matter. Albert Einstein's theory of relativity strengthens the case. His theory says that just as a lens bends light, a large mass in outer space, such as a cluster of galaxies, bends light travelling near it. This is known as gravitational lensing. The bending affects the light reaching us, distorting the image we see of whatever lies beyond the mass. The good news is that lensing occurs whether we can see the mass or not. That means we can detect dark matter within a cluster of galaxies from the distortion it creates in the images we see of more distant galaxies. This is a cluster of galaxies called Abell 2218. The thin arcs are actually images of galaxies far beyond this cluster. Each of these images is showing distortion, dominated by huge amounts of dark matter within 2218. Gravitational lensing lets physicists map out detailed distributions of dark matter in vast regions of outer space. In this image, entire galaxies appear as individual white spots, dark matter as pale blue shapes. Putting together what we've learned from the orbital, brightness, and lensing methods, there's strong evidence for the existence of vast amounts of dark matter within galaxies, as well as between them. But knowing the dark matter takes up vast portions of the universe still doesn't tell us what dark matter is. Maybe dark matter is made up of planets. They're hard to detect because they only reflect light. Maybe we've failed to see a lot of planets in distant galaxies. The Sun makes up 99.9% of all mass in our solar system. That leaves only 0.1% of the total mass for all the planets, asteroids and comets in the solar system. This means that if dark matter were made up of planets, there'd have to be thousands of planets the size of Jupiter for every single star in every galaxy in the universe. But our solar system has only 8 planets, not thousands, so it seems very unlikely that planets account for all of dark matter. Another possibility is that dark matter is made up of brown dwarf stars. They're bigger than planets, up to 10% of the mass of the Sun. And they're also hard to detect because they don't shine. Black holes may be another possibility. They have so much mass that even light can't escape from them, making them a likely candidate. These two possibilities can be checked out because we can detect brown dwarf stars and many black holes using gravitational lensing on a smaller scale. Instead of looking at distortions in galaxy images within clusters, scientists measure the temporary brightening of individual stars brought about by gravitational lensing. Using this technique, we can account for some dark matter, but not all of it. There's also another way physicists can estimate how much of dark matter is made up of black holes. The explosions that take place when they're created spew out readily detectable heavy elements. From the amount found, they can estimate the total mass of black holes in the universe. These calculations indicate that black holes only account for a small fraction of dark matter. Having ruled out planets, dwarf stars and black holes as making up the bulk of dark matter, scientists looked at a number of other ideas that also failed to deliver. So what other possibilities could be considered?
Maybe we got the picture completely wrong about the universe and we should be open-minded.
Some physicists think there is no dark matter.
Either there is something we haven't seen, some dark matter or whatever, or the theory of gravity is wrong. So people work on modified gravity, attempt to explain anomalous behavior in the universe, modifying Einstein's theory of gravity.
These scientists think the orbital method can't be used accurately on something as large as a galaxy.
I think dark matter really has holes in it. And it's possible that these alternative theories of gravity could correct those holes.
They think that when it comes to galaxies, Newton's law of universal gravitation needs to be modified.
Every time something doesn't work in the sky, you basically either say our theory of gravity is wrong, or it's just there's something out there we can't see.
Changing the laws of physics is a pretty radical step. But it wouldn't be the first time it's been done. Still, any new law of gravity would have to be rigorously tested before it's accepted. most physicists are confident that our current ideas about gravity are indeed valid for something as large as a galaxy.